In this video, we will make use of the two results presented in the previous video in order to identify the corresponding discrete time transition matrix for a continuous time model. We will do this both for a general linear system as well as for two important examples of the translational motion model, the constant velocity model and the constant acceleration model. We will start by looking at the general solution for linear systems. Suppose the continuous time motion is described by this linear differential equation, where a tilde here is a constant matrix and q tilde of t is a noise process. How should we then select the transition matrix ak-1 in this discrete time motion model, where we have xk equal to ak-1 times xk-1 plus some noise? Well, we have two options. We could either use the Euler method to approximate x of t plus capital T as x of t plus t times the derivative of x of t. We should note here that x of t plus capital T corresponds to xk and that x of t corresponds to xk minus 1. So all we need to do is to look at this equation and identify the matrices that we multiply x of t with. And that will give us ak minus 1, our transition matrix. In this case, we have x of t here, which is multiplied with an identity matrix. So we have I here times x of t. And then we have x of t here, which is multiplied by t times a tilde. So our transition matrix for the discrete time system, ak minus 1, is then I, the identity matrix, plus t times a tilde, where a tilde here is our transition matrix for the continuous time system. Another alternative is to make use of the exact solution for x of t plus capital T that we also derived in the previous video. According to that expression, x of t plus capital T is equal to e to the power of a tilde times t times x of t plus this integral here, which does not depend on x of t. If we again recall that x of t plus capital T corresponds to xk and that x of t corresponds to xk minus 1, then we can simply compare these two equations to conclude that our transition matrix ak minus 1 is equal to e to the power of capital T times a tilde, which is this factor here in front of x of t. If we compare the two solutions, the Euler method and the exact solution, we can see that the Euler method actually corresponds to the Taylor expansion of the exact solution if we only include the first two terms. I would also like to point out that normally it's better to use the exact solution than the Euler method, but I think the comparison is interesting since the Euler method is easier to apply, especially for nonlinear systems. Now, given these solutions for a general linear system, let's make use of this in order to compute the transition matrix in two examples. We start by looking at the so-called constant velocity model, CV model. Here we assume that we have a position state denoted p of t and a velocity state denoted v of t. Ignoring the noise component, it is assumed that the time derivative of the position state is the velocity and that the time derivative of the velocity is 0. That is, we assume that the velocity is constant and hence its name. If we write this on a matrix form, we have the following. So we have the time derivative of our state, which we denote at x dot of t, equal to this vector here, which is then equal to a matrix a tilde times x of t, which is this vector here, plus some noise. If we ignore the noise term here for a while and focus on this deterministic part of the model, if we look at the first element of x of t, which is p of t, we have that p dot of t, which is the time derivative of p, is equal to 0 times p of t plus 1 times v of t. So unsurprisingly, we're saying that the time derivative of the position is the velocity. Similarly, if we look at the time derivative of v of t, we're saying that it's 0 times p of t plus 0 times v of t, which is 0, right? So we're saying that the derivative of the velocity is 0, which is exactly what we wanted, right? So, according to this deterministic part of the model, the velocity can never change. That is, it is constant as the name suggests. Now, that's not a very realistic nor useful model. To allow for the state to deviate a bit from this, we add this noise term here, which typically actually only affects the velocity term here. That is, it's common to assume that q tilde of t here is actually a scalar noise process that can be written like this, where qc of t is a scalar white noise process. Now, with this added noise term here, we're actually saying that the velocity is nearly constant and that changes in the velocity is modeled as this zero mean random noise process. To the right, we have an illustration of one realization of this model. You can see that the velocity here is changing slowly and more or less randomly at each time instance here. We can see that the position state is then the integration of this, and we can see that it can more or less be described using piecewise linear segments, like this. So that is segments where the velocity is constant, as the model suggests. Now, could you think of a situation where it would be reasonable to use this model? One example that I think about is if we want to model a vehicle cruising on a highway, for example. In this case, the vehicle is keeping a fairly constant speed and not making too complicated maneuvers, which would match pretty good with the modeling assumptions that we have here. Even though we are discussing this model in terms of position and velocity, this model is not restricted to be used in a positioning problem. It is in fact suitable to use this model in any context where we have some underlying trend in our state, such we have this linear changing in our state, so some sort of trend here that we wish to capture. As you will see later, this could, for example, be a drift in our sensor that we wish to compensate for. So this type of model has many uses. So now we know all about the continuous time constant velocity model. Our objective here is to find a transition matrix, ak-1, for the discrete time constant velocity model. From the previous video, we know two ways of doing this. We have the Euler method and the exact analytical solution. Finding the solution to the Euler approximation is simple. We just plug in a tilde into this equation here. So we have the identity matrix plus t times a tilde. So we have the identity matrix here plus t times this a tilde here, and we get this transition matrix here. Furthermore, finding the exact solution is also trivial. If we plug in a tilde in this expression here, which we can express by this sequence here, so if we evaluate each term in this sequence, we have the identity matrix plus a tilde times t, which is what we got up here, right? Now the third term here, we have a tilde squared, which happens to be a zero matrix. So if we multiply a tilde with itself, we get all zeros out. And if a tilde squared is zero, then all the higher order terms here are also zero. So we simply get this result here, which is this matrix here. So what we can see here is that this is actually the same as that we got with the Euler method. So both methods gives us the same result. Now we can understand this mathematically as the second order term or higher are zero, but we can also think about it more intuitively by considering the approximation that the Euler method does. Namely that it approximates the time derivative as constant between two sample times. Now in this case, that's actually not an approximation, because if you look at this, the time derivative of the position is 0 times v, where v is actually constant. So this part here is just a constant, which is why the Euler method is the same as the exact solution. So the deterministic part of the discrete time model says that the position at time k is just the previous position plus t times previous velocity, which makes sense, right? And the velocity is just 0 times the position plus 1 times the previous velocity. So the new velocity is just the old velocity. So the resulting discrete time constant velocity model looks like this. So we have the position at the current time is equal to the position at the previous time plus t times the velocity, which makes sense, right? And the velocity at time k is simply the previous velocity. So it's constant. We will in later lectures also discuss how we can describe our discrete time noise process qk-1, but in this lecture we focus on the transition matrix. Another important example of a translational motion model is the constant acceleration model, or CA model. It resembles the constant velocity model, but in this case the state vector contains both a position, a velocity, and an acceleration state. The time derivative of the position is the velocity, but now that the acceleration is in the state vector, the time derivative of the velocity is assumed to be the acceleration, whereas the time derivative of the acceleration is instead assumed to be 0 plus some noise. We can write this on a matrix form like this, and if you multiply this together, you can verify that what I just said holds. So, the interpretation of this deterministic part of this model is instead that the acceleration is constant. Now, to allow for deviations from this, we add this noise term here, which is again often assumed to be a scalar white noise process, which we can write like this, where QC of t is a scalar zero mean random noise process. That is saying that the acceleration is nearly constant and that the changes in the acceleration is modeled according to this noise process, QC of t. To the right here, we have an illustration of one realization using this model. We see that the acceleration is allowed to change slowly and that the changes are more or less random. The velocity and position states are then the first and second order integration of the acceleration. But the velocity now changes more or less linearly, and that the position now then changes more or less quadratically as a function of time. So, when should we use this model? Well, compared to the constant velocity model, which could be applicable in highway scenarios at cruising speeds, the constant acceleration model would be better suited for when the vehicle's entering the highway and accelerating up to the speed on the highway. So, now that we know the continuous time constant acceleration model, how should we select the transition matrix ak-1 in our discretized version of this? Now, finding the Euler approximation for this system is again trivial. We plug in a tilde into this equation here. So ak-1 is the identity matrix plus t times a tilde, which becomes this matrix here, because the identity matrix has all ones on the diagonal, and a tilde has these ones here, so t times a tilde becomes these two off-diagonal elements. So if we try to interpret this discrete time model, we see that the current position is the previous position plus capital T times the previous velocity, but the acceleration state does not come into play here. For the velocity, however, we see that the current velocity is the previous velocity plus t times the previous acceleration. Now, let's compare this to what we get using the exact solution. Now, if we solve the problem using the exact solution instead, we get this Taylor series expansion of e to the power of a tilde times capital T. So we have the identity matrix plus a tilde times capital T plus a tilde squared capital T squared over 2, and so on. For this example, it turns out that all these three are non-zero, whereas a tilde to the power of 3 and up are 0. What happens is that this term here adds this element here, t squared over 2, which tells us that acceleration can also have an impact on our position, which is reasonable, right? We integrate acceleration twice to get an adjustment of our position. If we compare to what we get with the Euler method, then this term here is not present, right? This is 0 here. So normally this is the transition matrix that we recommend that you use if you like to use a constant acceleration model. But it's interesting to see the difference in the results as we tend to use the Euler method for when we have nonlinear models. So in this case, we see that there is a difference between the exact solution and the solution that we get with the Euler method. We can generalize the constant velocity and constant acceleration models that we just seen to higher dimensions. If we assume that the motion in the different dimensions are independent, this generalization is essentially trivial. If we do it for the constant velocity model, we can stack all the position states in the beginning and then afterwards have all the velocity states in the different dimensions. A tilde for the continuous time system looks like this, where In is the identity matrix of dimension n, and these zeros are assumed to be zero matrices of dimension n times n. If we plug this A tilde into the exact discretization model or the Euler approximation, we get this time discrete transition matrix. So it has the same form as we saw before, but everything here has been replaced by matrices. Now we can do a similar thing for the constant acceleration model, and we get this result here for the exact method. And we can also generalize this to arbitrary many dimensions, but normally we only do this for 2 or 3 dimensions. Here is a self-assessment question to find out if you can find the discrete time transition matrix for this continuous time model.